you're going to do a chain problem. So the picture's always the same. Actually, let's do this. No. I'll give you the easiest possible version. And then I'll give you a harder one that you can think about. Actually, no, I'm going to give you the easy one. I'm going to do an easy one. I'm going to give you an easy one, and then I'll give one that's a little bit harder. So the easiest version of this problem is you've got a chain of a certain density. I'm going to call it 5 pounds per foot. And you have a length of the chain. Let's say this chain is 100 feet long. And then what's going to happen for this problem is after I'm done, I'm going to be up here, and the entire chain is going to be at the top of the building. So I hold up the entire chain to the top of the building. And the question is, how much work did I do? So there's various slogans you want to remember. Is what's the definition of work? How do I find work? Exactly. Work is force times distance. What's a moment? So I guess there's 3 we have. What slogan you want to remember for a moment? Distance times. Yeah, distance times weight, or remember weight and area, essentially the same thing. So distance times weight or distance times area. And the other slogan you want to remember is force. How do you calculate force? It's 3 things multiplied together. Density times depth times area.
Johnny Depth.
What's it?
Johnny Depth. You know, he's Jack Sparrow under the water. You know.
That's exactly where it came from. People know that. Okay, but so for work, remember the work calculation is force times the distance. And the problem is, the part of the chain down here travels at a much greater distance than the part of the chain up there. So different parts of the chain travel different distances. What's the calculus solution to that problem? Let's chop it up into infinitely many pieces, do the calculation of the work for each of the pieces, and then add them all up. So we need a coordinate system to index the pieces. And this coordinate system is all we needed was a y direction. So different people do this differently. And so I like to put y equals 0 at the bottom and then have positive y go up. If your book will put y equals 0 at the top and have positive y go down. So different people have different ways they like to do it, all of which are allowed. So I'm trying to get my slice of the chain up here to y equals 100. My slice is down here, and y represents how far off the ground this slice is. What are the units for force? We say work is force times distance. What are the units for force? Pounds. It can either be pounds or newtons. And the USA version is pounds. The superior version is pounds, right? And really what that force is the force of gravity. So gravity is applying a force to this, it's pulling it down. And that's how we measure the pounds. Now, the only measurement up here I have that has pounds in it is this 5 pounds per foot. So I know that I'm at 5 pounds per foot. And what do I multiply pounds per feet to give me pounds? What unit? Feet. So how many feet tall is my slice? It is dy. So for the force times the distance calculation, the force is 5 dy pounds. The very bottom slice has to go up by 100. But if we give it a head start of y units, how much is left? 100 minus y. So this distance is 100 minus 1. So the distance calculation, 100 minus y. And I think I'm pretty casual about a lot of things, but the one thing I am going to have points deducted for is not having the dy at the end. So it's important to think about these as bookends, because these essentially work like parentheses. This tells you to find the antiderivative of the function that I'm going to start writing here, and then you stop. This dy is the other end until you when that function stops. So I do want the dy on the other end. And then we cut this chain into slices. What's the y value for the very bottom part of the chain? And the y value for the top? So I'm going to give you a slightly different problem. I'm going to give you two problems, actually. So here's you on the top of the building. And the building is still 100 feet tall. But now you only have 30 feet of chain. And the chain is still 5 pounds per foot. So how much work to bring the entire chain to the top of the building? And how much work to bring half of the chain the first version is essentially the problem I have here. So you have the chain, and you're going to pull the entire thing up. And then a slightly harder problem is, what if you just want to do the work? You just want to pull half the chain up. Problems? Both of these would be reasonable test questions. So let's see how you do. wander around a little bit here. Ready for me? Or do you want to keep thinking? You ready for me? So would this problem be different if I had a 30-foot building or a 100-foot building or a 1,000,000-foot building? But all that really matters, that's not even needed. So I decided to put y equals 0. I mean, you could have done it the other way. You want to do it that way?
Yeah.
Okay, sounds good. We put y equals 0 wherever we want. So we're in control, right? So if you put y equals 0 at the bottom, then the top of the building is at y equals. And let's bring over here. So the basic idea for this whole chapter is cut it into slices. So one slice needs to get up here to y equals 100, and my slice is there. And what y represents is, so y is the distance that slice is from the ground. So one bad thing about exams is you're trying to use your higher level, your executive functions for that. And once you start panicking, that's the more reptilian part of your brain, and the higher level shuts down. So if you ever get into that panic mode, it's just too hard to think about math because your body is trying to save itself. So to relax and get back down to it is there's certain phrases that you want to remember. So when I hear the word work, what do I think?
Math.
Force times distance. And how I'm measuring force in this problem? Pounds. And remember that in this context, we're fighting gravity. So that force is the force that gravity is pulling down on that. So for the force, which I'm trying to measure in pounds, I've got my 5 pounds per foot. And then how many feet is this? It's dy. So the force part is 5 dy. And I'm trying to get it up to y equals 100. I got a head start of y. How much is left? 100 minus 1. I do want to see that dy. It's the very last thing. And then you said it already. But what's the y value that starts the slice at the bottom of this G? 70. And we're going to keep adding these up until we get to y equals. Everybody good with that part?
Yeah.
For that second question, do you see that the slices near the top travel a fairly short distance, but the slices near the bottom all travel the same amount? Yes? Like really yes? Okay, so there's 2 types of slices here. There's the slices that travel a variable amount, and there's the slices that travel the fixed amount. So we're going to have two separate integrals. The variable, so I'll write it this way. You know the question. Give myself some more room right here. And so we're going to have one integral for the variable distance, and we're going to have one integral for the fixed distance. And then adding these two together, we'll figure out the work for each part, and adding those two together is going to give us the work for the entire thing. So the variable distance is exactly going to be this picture. So the variable distance is the integral is going to look the same. It's 5 times 100 minus y dy. If you remember, we're only pulling up half the chain. So what are the y values that correspond to the ones that get pulled up with variable distance? It's clearly the top, y equals 100 is that. Does y equals 90 go up a different distance than y equals 89? Yeah, so what's the y value where they're all going to go different distances? I'm going to go 85. So what happens is we're splitting this chain into two halves, the 15-foot top half and the 15-foot bottom half. So from 85 to 100. And then for the fixed distance, that's going to be the slices from 70 to 85. In what part of this integrand, the 5, the 100 minus y, or the dy, represented the distance? The 100 minus y. So everything on the bottom, remember we're just pulling half the chain to the top, everything on the bottom goes up by how much? So the distances for those are all 50. And a second way to do that one is you can also consider the bottom of the chain to just be a dead weight. So the bottom of the chain weighs 15 feet times 5 pounds per foot, which is 75 pounds, going up 15. So, does that feel okay about the work problem? So I think this is the most efficient use of our time. Is you tell me what type of problem you want to do. I'll do one myself just to remind you how to do it, and then you do a couple versions of it to make sure that you're comfortable with it. Okay. So what other topic? The area between two curves, volumes with discs and washers, volumes with shells. We can.
You're fun.
Actually, no, you know what? It's a disc is a washer with a hole of size 0. So I can do two separate volumes, one with a washer and one with a disc. You want to do it that way? So what's easier, disc or washer? Disc. So I'll do the easiest version. I'll give you one similar to the easy version, and then I'm going to do all hard. Problem might be is I describe something for you, and there shouldn't be any issue with graphing. Is either I'll have the picture for you, or the equations will be so simple you already know how to graph it. So it was Calculus 1 where I tested you on your ability to graph a function. Now, I'm testing you on something else. Actually, just with how I drew the picture, I'm going to change that to the y-axis. So I extend the y-axis down, and And I want to draw a rectangle in my original region so that when it rotates around the y-axis, I end up with a shell or a washer. So what would the orientation be? Horizontal or vertical? Horizontal. Okay, I went the wrong two. So this is what I'm going to rotate around. And when that rotates around, let's come up with something like this. And so I need to decorate it. Is this a dx or a dy? dy. And the rate, so that thickness is dy, and this radius is that distance. So that is x. So the volume of the slice is pi x squared dy. You always have to be careful with the clashes because we're doing dy. And so we have to get rid of that x squared. So what is x squared in terms of y? See, I actually set that up nicely. Is x squared is equal to y. So I'll write that as pi y dy. And then my integral adds those up. 0 to 2 or 0 to 4? Got the dy, it's telling me I'm picking y values. So that goes 0 to 4. So your problems, again, I'm going to give you a simple one and then a more complicated one. Is we use that same curve. Y equals x squared again. Same starting point. So each of those two shapes, I want you to rotate about the x-axis this time, and then figure out the volume of that shape, either using a disc or a washer. One of them is going to be a disc, one of them is going to be a disc with a hole in the middle that we call a washer. Two problems. An easy one and a hard one. ready for me, or do you want to keep working?
Ready.
You're ready? Okay. So the first one, remember the axis I want to rotate around is I extend out. I'm rotating about the x-axis. Favorite version of that. For the disc washer and shell problem, you've got a two-dimensional region, and your slice is going to be determined by a rectangle in the region. So if I want to make a disc or a washer, do I use a horizontal or a vertical slice? So I'm trying to make a disc, and that is the shape of the slice I want. And remember, I'm not going to grade your attempts that ended up going wrong. If you picked a horizontal rectangle, and then you tried to rotate that around, you got a weird shape like this, which is a shell. You just know that you picked the wrong one, you erase it, and you go back and pick the other one. So either you can see directly that vertical strip is the way to go, or make the wrong decision, the picture is going to show you that you were headed the wrong way. Rotate around, make one of these. Is this a dx or a dy? This is a dx. And for the radius of this, y. The volume of this slice is pi y squared dx. You see the flash there? What's y for this problem? So I fix it and integrate. And what are the limits of integration? Yes, they're x values, so that is 0. There's two ways I can make this type of problem harder. One way is to put that hole in the middle, so it's a washer instead of a disc. And another way I can make it harder is instead of rotating around the x-axis or the y-axis, rotate about a different horizontal or vertical line. So make sure you can do all of those. And a good way to practice for the test is, what I'd recommend is read the lecture notes first. Then, you notice that we do, those lecture notes are available on Canvas, so if you don't have them, they're on Canvas. You notice in class that we do a lot of problems. So I'd make a side notebook and just list out all the problems that we did for each section. Try to do it yourself. You don't know how to do it, go back, look at your notes. So you know how to do those problems by yourself. And then when you feel like you've mastered all the material, go to the practice test and try to take it without looking at any notes and see how you would have done if that was a real test. So those are ways to check in and see that you understand how to do these. And then what I do for more practice is just make up similar problems and do those. So I'm going to do the second one. Well, that's what I'm doing here. I'm just making up problems. And you should be able to generate similar ones yourself. So the second one is I'm rotating about the x-axis. Right? I'm trying to get a washer. What's the orientation of the rectangle that will give me a washer? Horizontal or vertical? For washer,